Now let us first review some very useful theorems on property. The Pythagoras theorem is very useful in solving related rates problem. The similar triangle property is very useful too, where suppose it's a smaller triangle with A and B length and a larger triangle, and they are similar really. So the ratio of a B over B prime is the same as A over A prime. This is a very useful property indeed. One more useful result would be the sine cosine rules. Here we have sine rules and the cosine rules. There's a very effective method for solving related rates problem. They're involving 3 steps mainly. Having read the questions, understanding the question, you should draw a diagram to illustrate the situation and label those variables and information. And then you write down the relevant equations. Well, just look at the questions and decide what equations to be written down. And then very often you require to differentiate this equation that you form in steps 2. There might be more than one. So here we look at a problem which requires the use of most of the theorems and property, and also allow us to use the steps to solve the related rates problem here. This is the trough has 6 meter, length 6 meter, has uniform cross section, and it is an equilateral triangle here. So the cross section is an equilateral triangle with sides 1 meter. So immediately we label the sides 1 meter, and water leaks from the bottom of the trough. Well, this information would be useful later, I suppose. And then find the rate of the water level falling at the instant that it is. This is a particular case, so we want to resolve for our general case first. And firstly, this is what we know. We know that the internal angle or interior angle is 60 degrees, including this one, 60 degrees. And suppose you're going to join the apex in a way to the base, then it is perpendicular, of course. Then we will get this part, half of angle at 30 degrees, and we may call that theta. Let's call that theta. So theta is 30 degrees. So theta is 30 degrees. Let me rub off those unnecessary ones first. No, we don't need this. Actually, I don't really need 60, so let me withdraw this. So good diagram is important. Perpendicular, and here is actually theta, and it is 30 degrees because it's half of 60, side 1. Now the water level, I might want to give a name to the depth of the water level, say let's call it H for height, and also I might want to consider something like X for half of this, so call this X, the radius of the water, something like that. Before we continue, just take a look at this. Here the particular case will be using something in cm, unit of cm, but this is in meter. So from now on we're going to convert everything to cm. So let us continue. Here we have the ratio of tangent is tangent of 30 degrees. Indeed, this is x divided by h, the opposite over the adjacent, and then we get x equals to h tangent 30 degrees. Now tangent 30 degrees is a special form of angle, and you have 1 square root of 3 times h. Now the volume is really, the trough will look something like this, in this shape in 3D. So the length is 6 meter or 600 cm. Remember, we're going to do everything in cm, and also so the length is 600 cm, but the the area of the cross section is given as the area of the triangle, and so the volume of water, or volume of trough or water that you can say would be equal to V, and that is an area of cross section times the length of the trough, and the area of cross section is really base times height, half of base times height. So we have, just for area itself, the half times 2x, because half is x, so the whole total length here will be 2x, and times h, and as for length, that will be 600 meter, or 600 cm rather. And finally, if you simplify this by substituting x equals to 1 square root of th into here, we would have 200 square root of 3 h squared. Of course, this is cm cubed. Now we have sketched the diagram and labeled it, and we have derived the equation that we required. The next step will be to differentiate these equations here. Now let's do that. Since because the rate of change of volume is respect to time, we choose to differentiate this respect to time too, and understand that h must be differentiated implicitly. And so we have dv dt. Here you have 233. Now to differentiate h squared, that will be implicitly 2h and dh dt. At the moment I skip the unit part. Now simplifying this, we end up with 433 dh dt. Now, piece of information is about the water leaking from the bottom of the trough at this constant rate, and so we know that dv dt is leaking, so it's negative 0.1 because this is leaking from the trough. However, notice that this is m cubed, a meter cubed per minute, and now we are actually calculating everything in cm, in unit of cm. So that would be 0.1, 100 to the power of 3, and cm per minute, rather cm cubed per minute, and in the end you have negative 100,000 cm cubed per minute. And the particular case here that we're looking at is when the water level is at 20 cm deep. So we are talking about what is the rate of change of h when h is 20. This is a special case, a particular case, h equals to 20. And what we do is we put this value and this value into this equation, or this differentiated equation, and we'll have let's do this, negative 100,000 for dv dt, and this is 403, and I think I've forgotten the h here. There's supposed to be h here, because after we simplify and replace the h with 20, and we have dh dt, because there's nothing we can replace it with, and in the end we'll have dh dt be equal to, if you perform the simplification, all this, something negative of 25 over 6 sub 3, and this is in cm per minute. So the water level is actually falling. It's falling, so water level is falling at negative 25 over 6 so 3 cm per minute when the water level is 20 cm.